Hello and welcome to my presentation on our paper, Forecasting Surface Particulate Matter During Wildfire Smoke Events with Spatial-Temporal Deep Learning. My name is Mohammed Saleh. I'm a graduate student studying computer science at the California State University, Los Angeles. And before we begin, I would just like to give a warm thank you to all my co-authors for their hard work and contributions. So, it's not controversial to say that wildfires are dangerous. There's been a stark increase in both the frequency and intensity of fire seasons. With this growing fire activity, smoke, which gets released when fire burns fuel, has become a more important problem to track due to its association with general mortality and negative cardiovascular outcomes. PM 2.5 from wildfire smoke alone is responsible for 24,100 all-cause deaths per year in the United States. But what is PM 2.5? What are surface particulates? Well, if we consider on the scale of a human hair, a single strand of human hair, that's about 50 to 70 microns or micrometers. Particulates are much smaller than that. PM10 is less than or equal to 10 microns, PM2.5 even smaller, less than or equal to 2.5, which means they're incredibly small and very easy for you to breathe in during a wildfire event, which is why, due to their size, they can go very deep within your lungs, which causes heart and lung effects, which is why it affects the cardiovascular system, because they get trapped deep within. Which brings us to why forecasting surface particulate matter is important. Given this rising threat, it is a matter of public safety to know where and when smoke could be expected to appear during a fire. And our goal, therefore, is a machine learning model that produces hourly 24-hour range predictions for surface smoke concentrations during wildfire events. And if you look at these two pictures here, you'll see the NASA Earth Observatory captured from space the smoke concentrations across the LA basin. And you can see a large amount of smoke clustering around the urban center. And pictured here by the Los Angeles Times, you can see on the surface just how dangerous this is. You can see the high concentration of smoke towards the north here. And anyone in this area who is inhaling this is at risk to develop heart and lung issues due to the particulates that are dangerous. So let's talk about the data. I won't cover every single data product, as there's a lot here, but I just want to give you a high-level overview of some of the most important ones. Starting with our target, what we're trying to predict, is the EPA air now sensor. And the reason we picked this is it has an hourly temporal resolution, which allows us to capture patterns and trends over an hour-to-hour basis. And more importantly, it's a federal grade reference sensor, which means it's a higher standard. It's the gold standard for ground sensors, which means we can trust its retrievals the most. Next, I want to talk about some of the meteorological features from NOAA's high resolution rapid refresh. We collect things like wind speed, wind direction. Wind speed is very important, for example, because when wind speed is high, PM 2.5 tends to go down in that specific area, but it also can transport it somewhere else, right? Because wind is blowing it in that direction. So whichever direction you and me are pointing and the magnitude of wind, we'll basically say wind speed may go down in this area, but will be blown upstream to another area. And the model can learn this, right? And when wind speed is down, for example, PM 2.5 tends to increase, right? Because it's not being blown away somewhere else. Next, I want to talk about GOES. Aerosol optical depth is a very important feature, as it measures how much light aerosols block through the atmospheric column. And the reason that's important is if it's very, very thick, that means there's a lot of aerosols, and aerosols are being released by something like a wildfire, right? So it's very thick. We can say there's a lot of smoke in the area, and the model can learn that, right? And then there's things like fire radioactive power, FRP, which measures the radiant energy coming off of a fire. So it basically says how strong a fire is, or if a fire is still smoldering or burning. And to begin on some of these data features, I just want to mention that most inputs, like GOES, Tempo, Modus, Aster, are 2D rasters in their native form. And each gridded channel is brought onto the same ecto-rectangular 84x84 grid, which means if you have a sparse network of air now sensors, say 18 pixels, and an 84x84 grid, That's not spatially complete, and there's some interpolation methods that we employ that I'll talk about in a second. But I wanted to mention that for things like wind U and V, these actually get rotated because they're in Lambert conformal. So we need to rotate them to Earth relative grid, an Earth relative coordinate system. So those are some of the pre-processing steps that we do here. GOES, AOD, and Tempo are actually only available during the day. It's another challenge we have with these products. This is because they are relying on reflected sunlight. So at nighttime, we actually don't have retrievals for these. And we'll talk about how we overcome that in a second. Next, I want to cover how we overcome the sparsity of our air and now network. Now, as I mentioned earlier, our target is composed of these sparse sensor areas. But what we need is a spatially complete grid, right? So the way we're going to overcome this is using interpolation to increase spatial resolution. So we're going to employ a method known as inverse distance weighting, specifically a 3D variant of this, where we include elevation in the z-axis. So essentially what we're doing here is each non-sensor pixel is interpolated from the nearest sensor pixel and is weighted by 1 over distance to the power. So what does that mean? That means, if you look here, this pixel here has a weighting of 12, this has a weighting of 10, and every single pixel away from an origin pixel is going to create this spatially complete grid and be assigned a weighting. The further you get from an origin pixel, the less influence it has, right? So you can see towards the middle here, this part's orange, but towards the back here, this part is more red. And you can actually see that occurring in our predictions, right? So you can see here on the left, we have our sparse readings. This one has a very high reading of yellow. And you can see these pixels here start very yellow. And as you go further and further away, they start becoming more green until they're dark over here, right? So you see every single pixel near the origin has high influence. Every pixel near an origin pixel is highly influenced by the origin. And as you get further away from them, that influence starts to go down. And this is how we overcome our spatial gap. Essentially, when we do this, we replace 18 pixels with a spatially complete grid. And now I just wanted to give some insight into how we assemble our input frames. And now I want to give some insight on how we assemble some of our data. So we take hourly retrievals of PM2.5 that have now been rasterized into IDW grids. We align them into contiguous 24-hour samples, and then we step through time 1 hour at a time between samples, creating a 24-hour sliding window with a stride of 1. So you see our sample 0 goes from hours 0 to 23, sample 1, hour 1 to 24, sample 2, hour 2 to 25. You see every single hour, we just slide the window over by 1, and this is what our model predicts on. And note that for satellite products such as Tempo and GOES, which don't have retrievals at night, we just do a static repeat to make sure that they're all temporally aligned. And in the end, we take all of the data products we've been talking about and assemble them into a 5D dimensional tensor, the shape of 24 for the horizon, 84 times 84 for the width and the height, and 26 for the number of channels. And note the 5th dimension, which we don't usually talk about, is just the batch. And this is what gets sent into the model. Next, I'm going to talk about the data augmentation we employed. Now, wildfire events aren't a rare anomaly. Big ones that are captured by the AirNow network actually are. So we've captured 6 or 7, if you consider August Complex 1 and 2, different fires, and we've employed a horizontal flip, vertical flip, rotation 90, rotation 270, and a transpose operation to every single data channel within the bundle, right? So all of these channels are being rotated and transformed together, which essentially increases our 5 times our data inventory from 854 to 5,124. And you can see here, really good agreement, right? You see the spike in PM2.5, you see the fire pixel, you see the smoke. And then if you do a horizontal flip, fire pixel, smoke, vertical flip, fire pixel, smoke. So you see that it's tracking for all of the data units. Our model is built on the convolutional LSTM, which embeds the convolutional operation within the LSTM itself, capturing both spatial and temporal patterns between features. A basic convolutional LSTM, however, proved too limited for smoke dynamics, so we added several components to bolster its predictive capacity, thus introducing the dual-branch convolutional LSTM. Now, the input is a 5D tensor of spatial temporal data, as I explained earlier, and that gets fed directly into the dual-branch encoder. And one of the advantages of having modeled meteorology is that it gives us future insight into the conditions we can expect for the next 24 hours. However, there is a challenge in communicating to the model that forecasted data is different to past data. So we just split them. And each past or forecasted bundle gets passed through their own branch with a COM 3D projection, a convolutional LCM 2D, and batch normalization before being concatenated back through a fusion layer. The model showed meaningful improvements when forecasted data was treated in this manner. The recurrent core, now we're in the middle, stacks 3 convolutional LSTM 2D blocks to expand capacity for learning spatial temporal patterns. The kernel mixes neighboring pixels at each time step, while the LSTM gate carries information across the sequence. The deeper a network becomes, having 3 blocks, the harder it is to maintain a good gradient flow, so we wrap each layer in a residual connection, giving the gradient a direct shortcut back to earlier layers. Now on the bottom, you'll notice this line here. This is the spatial PM2.5 scale. One of the primary reasons was the degradation of frames over time, along with predictions failing to respect the most recent PM2.5 values, which is an issue as there's a high correlation between the latest frame and the next 24-hour sequence. Finally, the decoder fuses that skip with the core output. Since the skip is a single frame and the core has 24 hours of latent space, we tile it across the temporal dimension, so every forecast hour gets the same anchor. The two are concatenated and passed through a convolutional LSTM 2D and batch normalization, where the recurrent cell learns how to combine the latent space representation for each hour with the anchor signal. A COM3D then projects down to a 24-hour sequence of PM2.5 forecasts across the full grid. In order to validate our results, we employed a leave one out cross-validation strategy. What that looks like is, say, if we have 6 fires in the data set, we train on 5 fires and leave 1 fire out and evaluate the model's performance of that fire. We did this for 3 such fires, each being very different to each other, allowing us to assess how the model performs under different conditions. So we had decided to use the August Complex Fire, the El Dorado Bobcat, and Palisades and 8 fires. And for each fire, we collected Pearson correlation metrics, RMSE, MAE, and sign bias, and we benchmarked this against 2 operational numerical models per smoke and NAQFC for a baseline to see how our model performs against other models out there. Beginning our analysis of the August Complex Fire, we're going to be using a 2D histogram plot. Beginning our analysis of the August Complex Fire, we're going to be using a 2D histogram plot. The x-axis is what the sensors actually measured. The y-axis is what the model predicted. And the diagonal line is perfect alignment, which means that the closer the points are to sitting on that line, the better the forecast. And if we look at the hard numbers here, we can see that convolutional LSTM is doing a much better job of forecasting than any QFC is, with a much stronger Pearson correlation of 0.617, lower RMSE at 34.08 in comparison to 118, and a Pearson correlation of negative 0.232. Lower MAE of 22.45 compared to MAE of 76.19. And if we look back here, August Complex convolutional LSTM tended to underpredict, but NEQFC tended to overpredict at a much larger magnitude. So while the model was underpredicting, it was still closer to the ground truth relatively speaking, magnitude to magnitude. And this is reflected in the time series, where we see on the left here, with the orange being our prediction and the black being the ground truth, that our model is able to follow the trends very well, and in some cases almost be right on top of it here, following it very, very closely. Compared this with NAQFC, where NAQFC appeared to overpredict most of the time, our model had much better agreement. Now looking at the Bobcat fire, this story is much more staggering. There's almost zero correlation with NAQFC in air now versus our model in air now. You see our model has 0.58 to NAQFC's 0.36. The RMSE here is a bit closer, but still our model is comfortably ahead at 23.85 versus 38.99. And if we look at the bias, we can see that our model is overpredicts a little bit on this fire, whereas NAQFC tended to underpredict by a lot, by -23 in comparison to our 2.61. See that? We can see that in the trends here. Again, our model is in orange, NAQFC in red. That our model tends to follow the prediction. That our prediction tends to follow the ground truth very closely. And here, if we look at the time series trends, we can see our model in orange following the ground truth. It seems to miss this peak here and then overpredict in this area, where her smoke tended to overpredict at the beginning and then underpredict for the rest of the fire, and did not seem to try to match its trend. And NAQFC was predicting massive amounts of PM2.5 and did not agree at all with the ground tensor network. Okay, finally, I want to just look at some of the qualitative frames to show you what the model is actually producing. So we see here, this is a set of 5 bundles, prediction versus ground truth, for the August complex fire. And we can see here that the model is capturing the trend of PM2.5 very well. It understands that in the northern region there is a spike. It seems to underpredict a bit here, and then tends to match the ground truth later on. Now, convolutional LCM models do have an issue where as time goes on, error compounds. So it is well known that the model will worsen its prediction over time. But still, we see even out 22 hours, that the model is still able to make strong predictions for this fire. Next, I wanted to look at the El Dorado Bobcat fire. This model relatively means good predictive capacity to at least 12 hours out. You can see here that the ground truth has a spike, and the prediction captures that spike. It even captures the second spike, although be it a bit under predicting. And then around hour 14-15, we can see that the model fails to capture this lingering spike down here, and there's a lot of model artifacting. And we see this trend continues for most of the fire. See that? Captures the prediction, and then it dissipates. So this fire, the model is able to have relatively good performance for at least 12 to 15 hours before failing to predict the spikes here at the bottom. And finally, the Palisades-Eaton fire. Our model has strong agreement And finally, the Palisades-Eaton fire. Our model tends to have strong agreement here, understanding where the spike is in the fire for most of the fire's duration. You can see here, here's the spike, and it does capture that quite well. It tends to overpredict at the end. However, as you can see in the ground truth at the bottom here, this area is spiking. It seems to over-exaggerate it just a tad. However, there was a lot of PM2.5 in this area, so this overall is a pretty strong aligned prediction to what we actually see occurring during the Palisades-Eaton fire. And that concludes our presentation. Our future work for this paper includes looking at other operational models, as well as other architectures to compare our model against, and other numerical models to see how they fare. Again, thanks for listening, and have a great day.